In this video, we'll look at practical techniques for the analysis of BJT circuits at DC. We know that the voltage-current relationships of BJTs are governed by the PN junction between base and emitter. However, these exponential voltage-current relationships are difficult to use for DC analysis. Therefore, we're going to make use of approximate models, similar to the way we use the constant forward voltage drop model in the analysis of diode circuits. We can also use a constant forward voltage drop model for the base emitter junction of BJTs. Thus, if this base emitter junction is not forward biased with 0.7 volts, we expect no current to flow. But if it is forward biased, we'll see current flowing for the NPN transistor shown here, and we'll assume, for our approximate analysis, a constant forward voltage drop of 0.7 volts. Now in active mode, we can therefore make use of the model shown in the top right. Here, we place a constant 0.7 volt drop between base and emitter, and we can use that constant voltage drop to find the currents that result in the BJT, knowing that the collector current is exactly beta times the base current, and that's captured by this current-dependent current source in the model. This active mode model for the NPN BJT will be valid so long as the analysis results in a collector-emitter voltage drop of at least 0.3 volts. That ensures that the collector-base junction is not forward biased, ensuring that there's no more than 0.4 volt forward drop between base and collector. Now, if the analysis reveals a collector-emitter voltage drop that's less than 0.3 volts, then we know that the transistor is not in active mode, and we therefore have to use a different model. Similar to the analysis of other nonlinear devices, such as the diode, if we're not sure which operating mode we're in, we can always make an assumption, proceed with the analysis using the model for that assumption, and if we've made the wrong assumption, we'll find that some premise of that model is violated. So, for example, we may find the collector-emitter voltage drop is less than 0.3. In that case, we know that our original assumption of an active mode BJT was incorrect, and we have to repeat the analysis all over again. And perhaps we might try assuming that the BJT is in saturation mode. In saturation mode, again, we've still got a forward voltage drop of 0.7 volts between base and emitter, assuming that there's forward current flowing there. But the collector emitter voltage drop now remains constant. And for our approximate model, we may assume a voltage drop of about 0.2 volts there. Again, sometimes slightly different values may be used. If we're deep in saturation, this voltage drop may be only 0.1. If we're on the verge, on the sort of the border between saturation and active mode, the voltage drop may be right at 0.3. As you can imagine, the difference in these assumptions, making these different assumptions might result in only a very small change in the overall current that's calculated. So again, using a saturation model, we assume a constant voltage drop between collector and emitter and find the collector current that results. The resulting collector current will no longer be beta times the base current. In fact, it'll be smaller than that, and we can then define the resulting ratio as the forced beta of the transistor in saturation mode. And again, just a reminder that the forced beta is not a constant. It depends purely on the operating point of the circuit. So these are the two approximate models that we can use in place of the NPN transistor for the analysis of the BJT circuits at DC. Finally, just a reminder that if there's no forward current flowing through the base emitter junction, then the transistor is simply cut off and there's no currents flowing. Similar models can be applied to the analysis of BJT circuits involving PNP transistors, except now the emitter-base junction will be forward biased when 0.7 volts arises with the polarity shown here. As long as that junction is forward biased, currents will be flowing to the base and collector, and whether the transistor's in active mode or saturation depends on its emitter-collector voltage drop. If that voltage is at least 0.3 volts, then we'll be in active mode, and the collector current will be exactly beta times the base current. And so the constant emitter base junction voltage assumption and this assumption of current ratio beta, those two assumptions allow us to calculate all the IV relationships in the circuit. If the emitter collector voltage drop turns out to be less than 0.3, then we must be in saturation, and we can adopt the model shown here. We may assume an approximate constant voltage drop of about 0.2 volts between emitter and collector, and then this simple model can be used to calculate the resulting currents. As usual, the analysis of electronic circuits is best learned by practice, so we'll go through a couple of examples here to illustrate the principles at play. Here's a simple schematic where all voltages and currents are DC quantities. There's nothing time varying here, so we denote the resulting currents and voltages here with uppercase symbols and uppercase subscripts. Remember, that's our notation for DC quantities. And we're asked to find the collector voltage and the emitter voltage with this NPN transistor and resistors in place. Now, just in case you're not familiar with the notation here, when you have a node labeled like this, that implies that it's connected to a DC voltage source with zero source impedance and a value of 4 volts with respect to ground. And over here, we've got a 10 volt source. So if we want to, we can redraw this schematic a little more clearly, showing those voltage sources explicitly. And that's what's done here. So we've got the 4 volt and the 10 volt source shown explicitly now. Just a reminder that you're asked to find here the collector voltage and emitter voltage. So given that, we've got 4 volts here with respect to ground, and the ground node is connected somewhere around the emitter, although of course there's a resistor in between, it's reasonable to assume that the base emitter junction is probably forward biased. So let's go ahead and make that assumption. And again, if we've made some mistake, we'll somehow arrive at a conclusion that invalidates the model. Let's go ahead and assume a 0.7 volt forward drop here. So right away we know that VE has got to equal 4 volts minus 0.7 volts, or 3.3 volts. So that's pretty straightforward. We've already got one of our unknowns found. Next step, well, let's call that step 1. Next step here is to find the emitter current. The emitter current is just found by Ohm's law. We've got 3.3 volts across the emitter RE, across the resistor RE. RE is 3.3 kilo ohms. So the emitter current is simply 1 milliamp. Next, we can find the collector current that's flowing. And the collector current is related to the emitter current by this constant alpha, which in this case is a value very, very close to 1. Given that beta is a value of 100, it's beta over beta plus 1, so it's about 0.99. So the collector current is very close to a value of 0.99 milliamps. And then finally, we can find the collector voltage, again using Ohm's law, right? The collector voltage is the 10 volts at this terminal of the resistor RC minus the voltage drop across the resistor RC when it's conducting a current IC. Now that's going to be 10 volts minus 4.7 volts, or 5.3 volts. So there's the two quantities that we were originally set out to find. Finally, if you're interested, you can also straightforwardly calculate the base current that's flowing here. Remember, the base current is simply the collector current over beta, so it's going to be given the beta is 100, it's going to be about 0.01 milliamps. So here's the same step-by-step procedure redrawn neatly. And remember, the whole premise of this analysis was that the transistor was in active mode because we assumed the 0.7 volt drop here. And we assumed that the collector current was beta times the base current. So we should do one final check on the analysis, which is, let's look at the collector emitter voltage here and ensure that it's greater than or equal to 0.3 volts. In this case, it's 5.3 minus 3.3 volts, so 2.0 volts, certainly greater than 0.3 volts. So our original assumption that we're in active mode was correct. And we're done. And here we've got essentially the same circuit, the one difference being that instead of 4 volts connected in the base, we've changed it to 6 volts connected in the base. And let's go ahead and repeat the analysis. So again, we've got a positive voltage between collector and emitter, it would seem. So let's use our constant forward voltage drop of 0.7 volts assumed for the base emitter junction. And this time we find that the emitter voltage is 5.3 volts. The resulting current that flows here, therefore, is higher than before. It's 5.3 volts over 3.3 kiloohms, which works out to about 1.6 milliamps compared to the 1 milliamp before. And that makes sense because the base is at a higher voltage, so we've got to cross this resistor here. Next step is to find the collector voltage that results with the collector current flowing through this 4.7K resistor. Now that collector current is very close to 1.6 milliamps, making a bit of an approximation there because really there's a constant alpha there, but alpha is about 0.99, so that's close enough. And we find that VC is 10 volts minus the voltage drop across this resistor, 4.7 kiloohms times the 1.6 milliamps, and it turns out that's about 2.5 volts. Now, hopefully at this point you would recognize a problem. The problem here is that we've done the calculation. Specifically, we've assumed that the collector current is equal to the emitter current times alpha, which is a constant very, very close to 1. That part of the analysis presumed that the transistor was in active mode. But in order for this transistor to be in active mode, this collector emitter voltage should be at least 0.3 volts. But in fact, it's below 0 volts, it's negative. So we're certainly not in active mode here. And therefore, the analysis needs to be redone, adopting a different model. So the calculation steps are just repeated here. But if we're not in active mode, then what's another possibility here? Well, we still do have what appears to be a forward voltage drop between base and emitter. So I wouldn't think that the transistor could be in cutoff. In fact, this transistor is in saturation. So no harm done. We just repeat the analysis, but this time we'll do it replacing the transistor with the model of a NPN transistor in saturation. So here's what that analysis looks like. In saturation, we've still got a 0.7 volt drop between base and emitter, and that still results in the same 5.3 volts in the emitter, the same 1.6 milliamp emitter current. But now what's different is that we no longer assume that the collector current equals the emitter current, or 0.99 times the emitter current, because we now in saturation have a forced beta that's less than the constant gain beta of the BJT in active mode. We don't know what beta forced is. We have to calculate it. But instead, what we do know in saturation is that this voltage drop is about 0.2 volts. So that's the second piece of our model that allows us to proceed in the analysis. So specifically, the next step is not to go straight to the collector current, but rather to go and find the collector voltage here. It's 0.2 volts above the emitter voltage, so that gives us 5.5 volts. And from there, we can go ahead and calculate the collector current. So specifically, we know the voltage drop here is 10 minus 5.5, or 4.5 volts across this 4.7K resistor, and that then allows us to calculate the collector current using Ohm's law. Right? The collector current is just under a milliamp because we've got 4.5 volts across 4.7K resistor. So it turns out it's 0.96. Okay, and finally we can calculate the base current. Step 5 here, in case you're wondering how that's done. That's just found as a sort of current conservation here. The base current has to equal the difference in current between the emitter current that's coming out and the collector current that's coming in. So we've already found the emitter current's 1.6 milliamps. We found the collector current 0.96 milliamps. The base must be providing the difference, 0.64 milliamps. And finally, if we were so inclined, we could find the forced beta. It's just this ratio of the collector current over the base current. In this case, it's certainly much less than 100. It's about 1.5. Okay. And you'll see here that there's nothing about this analysis that invalidates our assumption. The beta forced is certainly much less than beta, which is 100 for this transistor. You know, if we'd made a mistake here, and in fact this transistor wasn't in saturation, we might find a beta forced of 200, but that's just not the case. So that gives us some good confidence that we've done the analysis properly. Just do a second example here that involves a couple of new tricks. So here again, you've got a 15-volt source connected to the base, but now we've got these two resistors deriving the base voltage. This is a common circuit technique because this we'll see that this allows the base voltage to be biased somewhere below the collector voltage, but above the emitter voltage, without having to have a separate dedicated supply providing the base voltage explicitly. We can use the same, in this case, 15-volt supply for both, that's biasing both the collector and the emitter. So it's common circuit technique, but the analysis is a little more complicated here. A trick that can be used to simplify the analysis is to take the red boxed circuit here and come up with an equivalent circuit for it. Okay, so if we've got 100K here, 50K here, let's just consider this portion of the circuit. And if this is the output, we know that we can come up with an equivalent circuit here by finding the equivalent open circuit voltage here at the base, which is provided just by a straightforward voltage divider, right? You can easily calculate that this is 5 volts just by this voltage division ratio between the two resistors. So I'll replace this with a 5-volt source, and then a source resistance which is equal to the value that we would see looking back in here, which is if we set the independent 15-volt source back to 0 volts. So what's the resistance, Rs, that we see looking back this way? It's actually 50K ohm resistor in parallel with 100K ohm resistor. So that's 33 kilo ohms here. So this, we can take this simplified circuit and replace the red box circuit here on the left with it, and the analysis of the rest of the circuit remains the same. So we've gone ahead and done that in this schematic here. VBB is the 5-volt source we mentioned. RBB is the 33K resistor connected in the base. And this is, again, this is just a model for the real circuit, which we know is really 2 resistors connected to 15 volts. But we can use this equivalent circuit for the analysis of the rest of the voltages and currents, and we get the exact same value. So we're going to proceed now, assuming that the base emitter junction is forward biased, which looks reasonable because we've got 5 volts connected there in the base and ground connected in the emitter, albeit with a few resistors in between. But making that assumption, then we adopt our constant voltage drop model of 0.7 volts here. And the next step is to try and find the base and emitter currents somehow. So we're gonna do a kind of a mesh analysis here by equating the voltage drop through this path here from, I think it's better drawn this way, from VBB through the resistor RBB, through the base emitter junction and down to ground. We know that that voltage drop is 5 volts. So we can write an expression there. It says 5 volts is equal to the base current times 33.3 kilo ohms. That's the voltage drop across RBB, plus 0.7 volts, the base emitter voltage drop, plus the emitter current times RE, 3 kilo ohms. Now, the problem is there's one equation and 2 unknowns, but we know one other fact that allows us to relate the emitter and base current if we assume the transistor is in active mode. For now, that's an assumption. We'll have to validate that later, but if we proceed with that assumption, we can say that the emitter current is beta plus 1 times the base current. And we're given that beta is 100 for this transistor. So finally, we can write an expression completely in terms of IB. And rearrange this and solve for IB. Okay, almost there. Punch that in a calculator and you get about 13 microamps of base current here. So, the key fact here again was that we assumed the transistor was in active mode, and that allowed us to write the emitter current in terms of the base current and get an expression over here that's just in terms of IB. So in this slide, the analysis is completed a little more neatly. Again, there was a couple of key tricks introduced in the analysis of the circuit. One was replacing the base biasing network with a Thevenin equivalent source, the single resistor RBB. And the second trick was performing this analysis here by recognizing that the base and emitter currents are actually related by the transistor beta if it's in active mode. And so that allowed us to just write a single equation and solve for either the base or the emitter current we could have solved for actually here, you're following this path. So here the analysis is written out in detail. You see the 13 microamp current for the base here. The emitter current is about 100 times larger than that. Collector current's pretty much equal to the emitter current. And then finally, we can find the collector voltage here just by, again, using Ohm's law. The voltage drop across the 5K resistor is 5 kilo ohms times the collector current, 1.28 milliamps. So that's a voltage drop of about 6.4 volts. And that then allows us to find the collector voltage here. 15 volts minus 6.4 is 8.6 volts. So again, performing this analysis required us to assume active mode so far. So we want to do a final check. What's the collector emitter voltage here? Well, assuming it was an active mode, we arrive at a collector emitter voltage that's about 4.7 volts. And anyway, certainly much greater than the 0.3 volts that's required in order for our assumption of the transistor being in active mode to be correct. So we validated our assumption, all's well, and we've correctly solved for all the bias voltages and currents in the circuit. So do some practice examples on your own, and hopefully you'll get comfortable with these techniques.